In the middle of the Sahara Desert, there are places where no rain falls at all. At first glance, it seems that the only way to obtain large amounts of water here is through wells, pipelines, or expensive desalination plants. But German engineers found an unusual solution. They began producing water literally out of thin air. To do this, they installed massive mesh nets that look like giant fences. By morning, thousands of droplets of water have already formed on their surface. These droplets gradually merge into small streams and flow into storage tanks without pumps or complex machinery, providing water for entire communities. Today, we will explore how the CloudFisher technology makes it possible to collect millions of liters of water in places where it rarely rains, helping transform some of the driest regions on Earth. The Atacama Desert on the coast of Chile. In the late 20th century, the fishing village of Chungungo was left without a reliable source of fresh water. The local wells had completely dried up. Water was delivered to the settlement once a week by tanker trucks. Residents spent hours standing in line to purchase limited amounts of water. During this period, a group of researchers decided to conduct an experiment. They climbed to the summit of the nearby El Tofo mountain and installed flat, vertical plastic mesh screens there. Their goal was simple: to capture the dense clouds that regularly drifted in from the ocean. The results exceeded all expectations. The system began collecting up to 15,000 liters of clean water from the fog every day. For the first time, the villagers were able to plant gardens around their homes. However, this success came to an abrupt end because of a technical failure. One day, storm winds blowing in from the ocean exceeded 100 kilometers per hour. The flat mesh screens instantly turned into rigid sails. The metal support frames buckled under the immense pressure of the moving air. The steel support cables snapped and the plastic mesh was shredded to pieces within minutes. All the moisture collected from the fog bypassed the damaged gutters and flowed straight into the dry sand. The villagers lost their only source of water. The incident brought the development of the technology to a halt. Investors completely withdrew funding from similar projects around the world. Most experts in the field officially declared fog harvesting technology a dead end. Engineering agencies concluded that collecting water from the air on an industrial scale was simply impossible. Years later, German industrial designer Peter Trautwein began analyzing the failure. He carefully studied the damage to the Chilean installations and identified the key mistake. The force of the wind could not be resisted with a rigid structure. The system needed to be able to move. Instead of flat mesh screens, Trautwein developed a flexible, three-dimensional design. He assembled a team of engineers and founded the company Aqualonis. For several years, specialists tested different materials in wind tunnels at a laboratory in Munich. The result of this work was the CloudFisher technology. It is a specialized mesh made from durable monofilament fibers. The geometry of its openings allows hurricane-force winds to pass through the structure without creating a sail effect, while still capturing microscopic droplets of fog. To test his invention, Trautwein chose extreme conditions. The German engineers packed up the system's components and traveled to the western edge of the Sahara Desert. Their destination was the summit of Mount Boutmezguida in Morocco. The local population greeted the foreign specialists with skepticism, since rainfall had been absent in the region for years. It was here, at this elevation, that the new high-strength fibers would face their ultimate test against real desert storms. Storm winds at the summit of Mount Boutmezguida can reach speeds of 120 kilometers per hour. Powerful air currents slam into the CloudFisher's polymer fibers, yet the structure remains intact. Instead of being destroyed, it triggers a physical process that was once considered impossible in the Sahara. The mesh allows the hurricane-force wind to pass through while trapping millions of microscopic fog droplets within its three-dimensional structure. Moisture gradually accumulates, the droplets grow larger, and under the force of gravity, they flow down vertical gutters. At an elevation of 1,200 meters, the engineers collect their first supply of clean water. The calculations of the German specialists were fully confirmed. and the foundation of their idea came from a real story hidden in the Canary Islands. In the 15th century, Spanish conquistadors landed on the island of El Hierro. They discovered that the island had no rivers or lakes. Yet the local Bimbache people showed no signs of water scarcity and carefully concealed the source of their survival. The secret was a tree known as Garoe. The islanders hid the paths leading to it in order to prevent invaders from establishing a permanent presence in the region. When the Spaniards finally found the tree, they considered what they saw a miracle. Directly beneath the canopy of Garoe were stone reservoirs that were constantly being filled with fresh water. The tree supplied both the local tribe and the Spanish garrison with water until a powerful hurricane destroyed it in 1610. It took scientists another 3 centuries to solve the mystery. The Garoe tree did not produce water. It functioned as a natural fog collector. The island is constantly swept by moisture-laden trade winds coming in from the ocean. The laurel leaves efficiently captured tiny particles of moisture from passing clouds, and the condensed water flowed down the trunk. Peter Trautwein translated this natural mechanism into engineering calculations. The primitive plastic sheets used in 20th century experiments were replaced by a matrix-like structure that precisely replicates the physics of how the canopy of the Garoe tree distributes and captures moisture. But collecting water on a mountaintop was only half the challenge. The successful launch of the fog collectors created a new problem that nearly brought the entire project to a halt. The water was located on an isolated peak, while 16 Berber villages were scattered far below. Between the source and the homes stood steep rock faces with no roads and no power lines. Using electric pumps was impossible. Residents still spent up to 4 hours a day searching for dirty water in the lowlands. The engineers needed a way to deliver thousands of liters of water downhill without using a single kilowatt of energy. Otherwise, the system would remain nothing more than a useless monument to an ambitious idea. The arrival of a free source of water also intensified local tensions. Traders who had spent years selling water at enormous markups began openly opposing the construction of the new infrastructure. To save the project, the engineers had to develop a unique gravity-powered underground water distribution system. Laying more than 10 kilometers of pipeline through solid rock was done entirely by hand. Bringing heavy construction equipment onto the steep slopes of the Butmeguida mountain range proved impossible. Workers relied on hand tools, breaking through hard rock with picks and crowbars in 40-degree heat. Every plastic pipe had to be carried to the mountaintop on people's shoulders. This grueling phase required months of continuous physical labor, but it was what ultimately connected the high-altitude fog collectors to 16 Berber villages at the foot of the mountain range. To keep the network running, the Darcy Hamad Foundation placed local women in charge of the distribution hubs. Historically, they had always been responsible for securing water for their communities. Engineers from Aqualonis trained the village residents to monitor pressure levels and report leaks through text messages on their phones. Every point in the pipeline was equipped with autonomous sensors that transmitted data directly to smartphone screens. This eliminated water theft and allowed problems to be fixed without calling in European specialists. The pipeline operates entirely according to the laws of physics. The elevation difference between the mountaintop and the villages is approximately 500 meters. This terrain makes it possible to use gravity as the driving force. Water flows on its own, without generators or pumps that would require a constant supply of fuel. The natural slope creates a stable pressure of 5 bar throughout the system, ensuring a reliable supply of fresh water to remote homes. All pipeline sections were buried more than 1 meter underground to protect them from the scorching sun. The total area of the CloudFisher mesh network eventually reached 1,600 square meters. The launch of the system transformed life throughout the region. Before the pipeline was built, women spent up to 5 hours every day carrying heavy water containers from polluted lowland sources. These daily journeys consumed a huge portion of the Berber community's time and energy. After homes were connected to the CloudFisher network, the situation changed within just 30 days. Statistics showed that the time burden associated with collecting water was reduced by as much as 95%. Families also began growing vegetables on small plots of land right next to their homes. The engineers had proven that people could harvest useful resources from fog even in some of the world's harshest climates. But the Sahara had an extreme test in store for the system. Satellite radar detected the formation of a massive dust front deep within the desert. A powerful sandstorm with wind speeds exceeding 25 meters per second began moving toward Mount Boutmezguida. Tons of dust were lifted into the air to heights of up to 2 kilometers. If this dense cloud collided with the morning fog, the resulting muddy moisture would instantly clog the mesh openings. Under the desert heat, that layer would harden into a solid crust, blocking the flow of water to the villages. An orange cloud of dust completely obscures visibility at the summit of Mount Boutmezguida. The Saharan sandstorm reaches the CloudFisher installations. Monitoring instruments record a sudden drop in pressure throughout the pipeline network. The supply of fresh water to 16 villages comes to a halt within minutes. The stretched polymer mesh becomes coated with a dense layer of dry clay particles. The system completely loses its ability to capture moisture from the air. Without an immediate solution, the expensive installation could turn into a useless mass of dirt-clogged fabric within just a few hours. To save the project from shutdown, the German engineers turned to the survival mechanisms of organisms living in the driest place on Earth, the Atacama Desert in Chile. No measurable rainfall has been recorded in parts of this region for decades. The soil is almost completely devoid of life. Yet, biologists discovered isolated green zones in this extreme environment, known as fog oases. The only source of life for the local plants is a recurring ocean fog called camanchaca.
Scientists studied the structure of local cacti to understand how they protect themselves from accumulating layers of wind-blown sand. They discovered that the plants use a passive self-cleaning mechanism. The surface of the cacti is covered with microscopic wax-like cones. Desert dust cannot permanently adhere to them. The first droplets of fog condense on the tips of the spines, grow heavier, and roll down the stem. The water acts as a natural cleaning system. It gathers the accumulated dirt and carries it to the ground, instantly clearing the plant's pores so it can continue absorbing moisture from the air. German engineers partially replicated this natural process in the CloudFisher system. They positioned the metal frames at carefully calculated angles and applied an ultra-smooth coating to the polymer fibers. As a result, the installation can now operate autonomously during dust storms. The first 15 minutes of morning fog are used to wash away the dust that settled on the mesh. The resulting muddy water is diverted to the ground, bypassing the collection channels. As soon as the fibers are clean, perfectly pure drinking water immediately begins flowing into the reservoirs. CloudFisher proved that it could operate independently under harsh desert conditions. The project in Morocco continued providing a stable supply of fresh water to local communities. But when historians began examining archival records, they made a surprising discovery. It turned out that this modern technology is almost an exact copy of methods that were used thousands of years ago. The trail of these ancient inventions leads to the highlands of South America, where indigenous peoples were harvesting water from clouds long before the invention of modern textiles. In the Moquegua Valley of southern Peru, archaeologists discovered a network of stone reservoirs built along barren hilltops. There have never been any rivers in these upland areas, and groundwater lies more than 100 meters below the surface. Researchers were drawn to a series of channels that stretched along steep cliffs, positioned perpendicular to the path of moisture-laden clouds coming in from the ocean. Analysis of residue found at the bottom of the collectors revealed a startling date: 1101 AD. Centuries before the rise of the Inca Empire, the Chiribaya people had manually constructed a large-scale system for harvesting water directly from the air. Their builders placed water collectors in narrow mountain passes where the terrain naturally accelerated the wind. They planted trees with dense canopies along the ridges, or erected barriers made from reeds. Microscopic droplets of moisture became trapped in the branches. The accumulated condensation flowed down the trunks into stone channels that carried the water to underground cisterns. The stone lining protected the stored water from evaporation during the hottest part of the day, when surface temperatures could reach 35 degrees Celsius.
These communities supplied entire settlements with water and irrigated agricultural terraces in the middle of the desert. The physics behind this process is virtually identical to the operating principles of the German CloudFisher system. 20th century engineers essentially recreated the methods of these ancient builders, replacing organic materials with durable, high-strength polymers. This made it possible to scale the technology. Networks of vertical fog harvesting meshes were later deployed in Yemen, Oman, South Africa, and Chile. In the Indian state of Gujarat, similar installations became a primary source of water for rural communities during periods when monsoon rains failed to arrive. The cost of producing a liter of water through this method proved lower than the cost of desalination. The simplicity of the design made it possible to deploy new modules in just a few days, giving remote villages independence from centralized water infrastructure. But the large-scale adoption of passive fog harvesting systems eventually encountered a climatic factor that could not be solved through engineering alone. Satellites have detected changes in the paths of cold ocean currents. In key regions where fog harvesting systems are used, the density of morning moisture has begun to decline. Annual measurements show that the amount of water vapor in the air is decreasing by about 3% each year, reducing the efficiency of the collection arrays. Designers now face an urgent challenge. They must redesign the geometry of the CloudFisher mesh to capture even highly diluted moisture. Engineers at Aqualonis have already begun modifying the fiber structure in their Munich laboratories. They are testing new materials and designs on specialized rigs that simulate the conditions expected under global warming. And now, we will see how these new technologies could reshape the global distribution of fresh water. Water vapor rushes through the polymer mesh at high speed, leaving almost no droplets behind. As the climate changes, coastal fog banks are becoming less dense, and microscopic water particles are shrinking in size. Under these conditions, earlier versions of the CloudFisher system suffer a significant loss of efficiency. Engineers faced a new technical challenge: how to capture water droplets that have become almost invisible. In their laboratories, specialists at Aqualonis launched a series of tests aimed at redesigning the geometry of the collection mesh before mountain communities begin experiencing water shortages. The team completely reworked the fabric's weaving pattern, creating a new three-dimensional matrix. The design consists of multiple layers of mesh, with extremely fine monofilaments positioned at minimal distances from one another. High-speed airflow can still pass freely through the structure, but even the tiniest particles of water vapor are now reliably captured by the fibers. The upgraded system can withstand storm winds exceeding 120 kilometers per hour, while transforming sparse condensation into a steady flow of clean, fresh water. The engineers proved that precise design and calculation can overcome the effects of changing climate conditions. The global success of the upgraded technology unfolded before the eyes of hundreds of delegates. In 2016, at the United Nations Climate Conference in Marrakesh, the Moroccan project received the prestigious Momentum for Change Award. Experts officially recognized the installation as a benchmark for environmental sustainability. Monitoring equipment recorded thousands of liters of pure drinking water flowing into storage reservoirs completely on their own, without electric pumps, generators, or fuel consumption of any kind. This recognition changed the balance of power on the world's environmental map. Upgraded CloudFisher systems began appearing on steep mountain slopes in Eritrea, Colombia, and Jordan. Arid regions, where people had struggled with water shortages for centuries, gained a new level of independence. Residents no longer had to wait for rare rainfall or drill expensive wells that deplete underground aquifers and contribute to soil salinization. Instead, passive polymer mesh systems capture moisture directly from the sky, restoring a reliable water supply to some of the most isolated places on Earth. The evolution of fog harvesting had reached a new stage. By combining the durability of modern polymers with the laws of physics, engineers transformed a natural phenomenon into a dependable source of drinking water. CloudFisher proved that saving thousands of families does not require complex digital systems. While you were watching this video, Installations on mountain slopes around the world collected dozens more liters of clean water from the air.